Part 2 video podcast for field methods in hydrology related to the topic of water velocity measurement. What I want to do in this video podcast is present a variety of different methods for measuring velocity. And in order to do that, I just want to make the point that unlike some other things, there really is no one way that is just absolute best in all cases. To some extent, there's a gold standard in terms of what's tried and true with point-based measurement, but the technologies have come on very strong for what we now call profiling methods that are very powerful as well. And I just have to say that I don't think there's one thing that you're just going to buy that one and it's going to solve all of your problems. On the other hand, we've seen somewhat of a consolidation in the market, unfortunately. There are fewer companies today than there were in the recent past, and in a way that hurts because I think overall the prices have gone up significantly, and that has made it a lot harder. The first method, as always, I like to start with the simplest approach, and that's just the float method. It's the old just throw something in the water and measure how long it takes to travel a known distance. Now, of course, to do that well, as illustrated in this schematic to the right from Sanders 1998, it does take a little bit more effort and thought. Sometimes you need to demark the distance you're going to measure. I mean, this is a very fancy sort of thing. Probably aren't going to necessarily do that. You have to decide, though, are you going to measure once, or you're going to measure in multiple locations? Something to think about. But basically, all velocity is a distance traversed through time. So with a literal interpretation, you can use a float to get that. Of course, this is very cheap. You can go anywhere in the world, regardless of technology. If you have a watch and a banana peel, then you can do this method, or just a leaf or a stick from along the side of the river so you don't contaminate the river with organic bananas. There is now a far more advanced method to do this. It's something that I've been doing a lot myself, actually, and other people have been doing. It certainly isn't something that I came up with. But the idea is that you just take a GPS, and remember, a GPS measures your position. So if you can put a GPS in a waterproof bag or on some kind of floating, platform or boat, and if that is moving with the current, then simply let it take your measurement every 5 seconds or so, and it will be recording its position at that time interval. So all you have to do then is apply the formula for computing distance in an XY or XYZ coordinate space, and you can get the change in distance through time. Now that sounds complicated, I guess, but all that distance formula is, remember, it's the square root of x1 minus x2 squared plus y1 minus y2 squared. So the square root of all of that. That's just your standard distance formula. And just divide that by your sampling interval, and you have a velocity that represents the overall velocity over the distance traversed. With both of these approaches, you do suffer a little bit in that the object that you're using for the float method, it's mostly going to move with the water, but as a solid object, it will carry its momentum so that if the water slows down, it will continue to project at that current speed. On the other hand, if the water speeds up suddenly, it will take longer to speed up. So the more the object is well, immersed into the top of the flow, the more it's going to represent that overall surface velocity. Also, the smaller the object, the closer its density is to that of water. On the other hand, if you have a boat like a kayak or something, where you can manipulate the boat to keep it at the same speed and direction as the current, like by throwing a bunch of, like twigs or grass or something around the boat as it's moving, then you can very effectively maintain a speed and direction that's the same. And so with this advanced version of the float method, not only are you measuring the speed, but you can also get the direction, because you can use, if you have two positions in time, then you can compute the vector between those two and get the compass direction and therefore the velocity components in the x and y direction. So it can get fairly advanced today, and so it's a pretty solid method to use. The biggest disadvantage of this method is that it's giving you surface velocity. which isn't the same as, of course, mean velocity. And for most applications, we want mean velocity. Another thing is, of course, when you're doing this, you're not getting the depth. So that's a problem too, because lots of calculations would require depth. And as you'll see, many methods measure depth at the same time as velocity, so that's a little bit of a disadvantage. The surface velocity classically has been said to be about 0.8. I'm sorry, well, no, the mean velocity has been said to be 0.8 to 0.85 times surface velocity, right? Remember, from the velocity profile, the velocity is fastest at the surface, so it's about 15-20% slower than surface velocity. However, I also showed you an example from the Mokelumne River where it was quite different from that. It actually had a value of 0.7 times surface velocity, and I've seen evidence that it could be as low as 0.6 in a very rough, shallow channel. So we really don't have a good handle on how to correct for that if you want to get mean velocity using the float method. But I still feel like, if you're in water that's extremely shallow and you can't get a velocity sensor in, the float method is it. On the other hand, if you're in a really big flood and you can't get in, or you're near the mouth of the Amazon somehow, you need a velocity measurement, the float method is what you're going to use. Well, far and away the most commonly used technology in the latter half of the 20th century, and still today in the early 21st century, is a propeller-based velocity meter. The propeller, there's two examples of that shown here, a vertical axis and a horizontal axis meter. And in both cases, when they spin one revolution, then what happens is a circuit is triggered. It's a lot like a tipping bucket rain gauge in that sense, like closing one circuit, so it's registering the event, but knowing the distance it takes to traverse for the fixed radius of the propellers, then you can compute the velocity based on that distance divided by the time it took between triggers. And of course, I'll be demonstrating these in class, so you can play with it and see how that works. So typically, these are mounted on something called a wading rod, so you can wade out into the river or stream and make a measurement. But they can also be deployed by boat on a cable that you lower by winch down into the river, or on a cableway, say, on a bridge or cableway that's over the river. Again, you lower down by cable. And that's why this upper sensor shows this fin in the back, that this helps keep it oriented in the direction of the peak velocity. The vertical axis is what's traditionally used more commonly in the US. It's a USGS style velocimeter. It has some advantage in that everything is protected inside these sealed areas, but it has a major disadvantage in that material can get hung up in the propeller. So if there's vegetation or sticks, I've had that experience where it can get caught in here. However, it's pretty remarkable. When you spin this, it almost feels like perpetual motion, like when this is really well maintained. But it also turns out that you have to open this and clean out and really maintain good functioning of this sensor. It's not a technology that you just take out in the field and then throw it back on the shelf on the way home. You really have to take care of it and know how to do that. So there is some expertise to that. The horizontal axis meter is more commonly used in Europe. It disturbs the flow less because it's more streamlined, and the axis is protected, so there's less chance of entanglement. However, you can see that in a comparative price basis, it's more than twice as expensive, almost 3 times as expensive for the European horizontal axis meters. And so that's another reason why often we just use the vertical one. In order to put this point measurement at the right location in the vertical profile, we use something called a top setting wading rod. Now this is a really remarkable piece of technology. It's really, I just love this thing. I mean, it's really cool. The idea that I can use a simple mechanical device with no calculation really on my part and get the sensor either at that 0.6 up from the bed, point 0.2 up from the bed or 0.8 up from the bed position in the water column. So depth is read on the graduated hex main rod. So this is graduated, this rod, it has like a hex shape, and you read the depth. You just put it in, look at where the water is, and read off the depth value. So let's say that you had a 30 centimeters depth. Then you come up to the top, and at the top for the metric one, it would be numbered 1 through 10, and you put it at the 3. There's like this round rod is also graduated, and you line the 3 up here with 0 on the side, and that would be the 30 centimeters. So this is something that's very hard to understand or grasp just from talking, and so we'll be playing with this both in class and in the field, and you'll get it in a minute. It's really a really simple and successful technology. It's really elegant. So you can position this at the 3 different locations that I talked about in the first part video podcast on this topic. Of course, there has to be caution with weighting. The rule of thumb for really good safety for people who are not highly experienced with wading in rivers is to avoid wading in water that has a product where velocity times depth exceeds 10. So that would be something like, well, okay, this is definitely a challenge. Sometimes you see a value of 6 here, so like 3 feet of water depth with 2 foot per second of velocity, something like that. I think 10 is a little bit more liberal value, but I can tell you, like, I was out recently wading in a stream, and I was in over 4.2 feet per second with about 2.5 feet of water depth. So it was over 10, but not by a lot. But the substrate was gravel and cobble that was pretty hard to maintain a position in. And so it's one thing to be able to stand there and hold position, especially because you're aided by the wading rod itself as like a third leg. But if you need to move around, that's a whole nother matter. So you really can't walk very well if the value here exceeds 10. And if you're really not experienced, you would want to lower this value substantially, like to 5 or 6. So remember that as depth increases, the force on you is based on the projected area. So staying in a perpendicular streamlined position so that the flow is hitting a smaller projected area is helpful. And but force is proportional to velocity squared. So going from 2 foot depth to 3 foot depth, not as big a deal as going from 2 feet per second to 3 feet per second. Also, once you get above, like you get chest deep in water, I've just sort of experienced a kind of buoyancy effect where you just start wanting to float, like unless you have weights holding you down, it's not just a question of direct force, but there's also that buoyancy force that your body's experiencing that, you don't feel when you're only 2 feet down. So that's another factor. So if you want to get velocity measurements in, flows that say, approaching bankful or of course in flood conditions, you're probably not going to be wading out into the river. Instead, you might put a platform across. If it's a small creek, you might put a bridge, like just lay a straight, sorry, not a bridge, a ladder, like put a like a fireman's ladder across it, and then, or maybe 2 side by side, and be able to go. Make sure you've tested this and know what you're doing in safe conditions before you go out during a flood, of course. But oftentimes we'll see temporary or permanent bridges and platforms or cableways that are strung across the river. So here's an example of a bank-operated cableway. And you can see that here we have a simple pulley system with a winch, and you can just wind this winch and go back and forth. So we have the pulley around the top, and then that's on one winch that helps to take this around back and forth. And then there's a second winch that has the line that goes through the vertical pulley and raises and lowers the sensor. Now this looks kind of weird because you've got like this bomb thing, and then there's the velocity sensor, number 6 here. What the bomb is a weight, because if you lower a velocity sensor, into a very fast moving current, it's basically just going to swing because it's on a cable. It's not going to stay vertical, and it's impossible to keep it truly vertical. But using a very heavy piece of metal in the shape of a bomb is a very meaningful, workable approach to try to offset that effect. Okay, the next technology to use is still a point-based velocimeter, but instead of having a propeller that requires a lot of maintenance or get clogged, it relies on an electromagnetic principle. In fact, in this case, the sensor itself is just a hunk of rubber. That's all you see. And what's happening is that inside of this, it's using electricity to create a magnetic field. And the voltage required to maintain that field in a certain condition is a function of the velocity of the water flowing around it. So the higher the velocity, then the higher the voltage needed. And so therefore there's a calibration between voltage and velocity that's done there. The best thing about this is, you're getting a digital, you're taking the analog signal, the voltage, and then running it into a digital readout and a digital data collection system. But what's so great about this essentially is just highly ruggedized and it has no moving parts. So there's no maintenance required. You have to be mindful that you can't put it into like an oil-water mixture. But other than that, if you're using it in natural waters, it's very straightforward to use, really simple. It's lightweight, it's got a digital readout, water resistant. It does require batteries, so that's, you just have to maintain that. Another thing about this that's convenient, and I guess it's something I haven't mentioned yet, is that when you measure velocity, you're not just measuring it for an instant. And I actually don't have a slide specifically about this. But typically when you're going to measure with either a propeller-based velocimeter or any other point-based meter, you need to record over enough time to average out the turbulence. So that could be 30, 40, or 60 seconds. I usually choose 40 seconds as a trade-off, but it just depends on how much the data is fluctuating. With this electromagnetic current meter, there's a time readout that just goes across, so when you can set how long you want to average over, and then it gives you both the instantaneous and average values. Notice in terms of cost, this is more expensive than the propeller meters, but it's still, it's still manageable, I would say. There's also a version of the sensor that can measure 2 dimensions. So normally these are just measuring into and out of the flow. There's also a version that measures the transverse horizontal flux in addition to the longitudinal flux. Now one thing is that the instrument that's shown here is no longer produced anymore. The company that made it, Marsh McBurney, was bought out. The thing about the Marsh McBurney meter, it's an accurate sensor, but it's not highly precise. So there have been studies that have shown that if you average over a longer time, then you get a very good, accurate measurement of velocity, but any individual value, of course, may not be right on. But nevertheless, this was the workhorse for decades, and now that was bought out by a competitor and discontinued. And now the replacement for that from the competitor is more than $1,000 above this cost. So we'll see how that changes through time. But of course, just in general, when you have a marketplace with fewer competitors, then you can expect prices to go up, not down. And you have to appreciate that there's a relatively small market of people doing velocity measurements compared to just buying a smartphone or something. So with that relatively small market, prices are inflated because there's a lack of demand. Okay, so here is the next technology that can be used to measure velocity, both at the point scale and averaging through space. The technology is based on something called the Doppler effect, which I'm sure you've already heard of, like Doppler radar or what's shown here. So I just need to explain the Doppler effect briefly. Doppler effect is the change in frequency of a wave for an observer when the source of the wave is moving relative to the position of that observer. So here is a visualization that shows a car, and as it's moving, you can see that it's like running into the frequencies, the signal ahead of it, which shortens the frequency, and it lengthens the frequency behind it. And just as an illustration of this, I also have, well, that didn't work. Okay, well, I had a video, but that video has been lost. So maybe I should just quickly turn my Wi-Fi on, and I like to turn that off so I don't get bothered in the middle of the presentation. But let's try this again and see if I can get this to work. And of course, it's gone. Let's see, history, example of Doppler effect. Just give it a second here. Sorry for not having this queued up the way I did. Okay, it's just a 10-second video, but okay. Okay, so that should give you a sense, like the higher frequency sound as it's coming towards you, and then lower frequency as it's moving away. Never mind the poor citizens who had to listen to that car go by, but that should give you a feel for the Doppler effect. So it's possible for velocity sensors to take advantage of that, and there's a couple different ways of doing that you'll find on the market. An approach that isn't used that much, but there is a few examples of it, is called this ultrasonic Doppler current meter. This is a sensor produced by a company out of Australia called Unidata, and you put it on the bed, and so that's already one flag, because if the bed is mobile or like fine sediment, it's not going to be so good there. But if your bed is a canal or a bedrock, cement, or even just cobbles, and it might work okay. You face it so that these two circles are pointing upstream, and you can see it's kind of bolted onto the bed or bolted onto a platform on the bed. And then it sends out an acoustic signal at this beam angle, and then that reflects off particles in the water. The particles could be air bubbles, could be organic matter or sediment, like whatever is in there. And what it does, it looks at all the particles that come back and produces an average from that. Now, of course, that does raise some problems, because what if there's an unequal distribution of particles through the water column? Then your average is not going to be representative. It's going to be reflecting where there's more particles. Or if the water is just so clear that there's no particles there or bubbles somehow, then it may not work very well. And there was a study that was done actually by the U.S. Bureau of Reclamation that compares a lot of different velocity sensors. Actually, it's very handy if you want to learn more about the pros and cons of these different methods to go take a look at what they've done. And what they wrote is that the StarFlow consistently computed discharges that were higher. However, because it was consistently higher, that means you could just do a calibration for how that would work. So what's nice about this that's very different from the other sensors is it's actually data logging. And it also has a pressure transducer in here, so it can measure water depth, and it can data log velocity. So if you need continuous measurements of velocity, this is really valuable. It's very, very useful technology. It's not the only one that does this. Sontec makes a more expensive, better version that doesn't just average through the whole column, but it actually is a profiler that has a similar either vertical or horizontal beam. And so that brings us to a technology called Acoustic Doppler Velocimetry, which is a point-based sensor that is based on the Doppler effect. But now, instead of averaging through the water column to get a value, it's able to focus on what's happening in a tiny cylinder of the water that is a certain distance away. So there's an acoustic transmitter, sends out a signal, and then within that sampling volume, there's reflections that go back to 3 acoustic receivers. And that actually gives you a 3D velocity measurement. So remember, velocity is a vector, a downstream component, a cross-stream component, and a vertical component. However, it's not oriented that way. I mean, of course, however you hold this sensor with its prongs, you're going to get a different, you'll get the 3D vector, but relative to its coordinate system, not the river. And this comes in both a weighting version, and I've got a few of those for use in class, as well as one that you can just mount like on a stick that you can use in a flume or in a permanent installation on a hydraulic structure. And these sensors can be anywhere from $4,000 to $12,000. Has all the same advantages as an electromagnetic point sampler, but it's 3D instead of 1 or 2D, and it's far more accurate. In fact, this would be the most accurate measurement of a point-based velocity. And notice that the sampling volume here is like 6 millimeters in diameter by 9 millimeters high. So it's a very, very small, area, and that has pros and cons. I mean, of course, the tinier the area is, then the harder it is to say what's the relevance of that over the river. Even if you're interested in a relatively small area, like a 1 meter cell, going from 1 meter and representing that with something that's like 6 millimeters by 9 millimeters is quite different. So that's the challenge. And then I think the thing that frustrates me the most about this kind of sensor is just simply the orientation. It's a challenge. You can't like look over at the bank and say, okay, now I'm like perpendicular to the bank. Banks are very complex. Unless you're in a canal, it's virtually impossible to do that. And you can orient the sensor so that if you're watching the digital readout, I can orient it to get to where the lateral component and vertical components are basically zero. So I know I'm right in the current. So I can orient it relative to the streamlines of the flow, but that's not necessarily perpendicular to the banks. And so that's a challenge. Okay, so I started to talk about this. I kind of backed off. Probably should have presented the velocimeter before the ultrasonic Doppler, but anyway, this is the full-blown acoustic Doppler current profiler. So compared to the ultrasonic one 2 slides ago that averages through the water column, this has the ability of giving us the whole profile. So if you look at the lower right here, I have a plot with depth on the y-axis and distance across the channel on the x-axis. I have a ability to read the depth along here from the sensor. And then the colors in the water represent velocity, with the reds being a high velocity of like 1.5 feet per second, and then the blues to purples being lowest velocities close to 0. In general, you can see the pattern that I've talked about with the highest velocity at the top and towards the center, lower velocities along the banks and the bottom. However, there's a lot of noise in here. I mean, there's a crazy amount of noise in here. And so this just illustrates the turbulent nature of the river and possibly some of the challenges of measurement as well. Here what you can see is they've actually taken the sensor and they've mounted it on a little bit of like, it looks like a kickboard. And they've also put a high resolution GPS on there so they can get position. Since this is a canal, they have a little bit of a cableway going across. And what happens is you just drag this across, moving at a relatively slow, constant speed across the channel, and it will make that profile as it goes across. This technology is primarily used for measuring discharge, but you can see it does give you a lot of velocity information as well. The typical price of a sensor like this is really $18,000 to $25,000, but there are cheaper models and there's more expensive models. Another thing you can see about it, if you look at this image in the upper right, is there's one beam that's going straight down. That's to measure depth. And then this is showing 4 beams that are going out at angles, and it's measuring the velocity in those beams. So this then raises a challenge in that first, you can see that as you go closer to the bed, the beam is spreading. And so you're measuring a variable sampling volume through the depth. Second, you've got 4 different beams, and so you're averaging all of those together to represent what's happening under the boat. And then third, if you look at this data in the bottom right, there's no data in the top 2.5 feet or the very bottom area. Now, I'm more concerned about the top area, and what's happening here is that when a signal is sent out, of course it has to reflect off something and come back. And so if something is so close, then in the time it takes to send out a signal, the receiver isn't ready to receive a signal as fast as it comes back for this area close to the bottom of the boat, close to the sensor. So there's this unmeasured zone where just the ping down and back is so fast it can't receive the signal, and there's trade-offs between how deep you want to go and what that is. I mean, for something like this, where you're blocking out, let's say 3 feet out of 30 feet, well, that's 10%. So 10%. I mean, it's a meaningful loss, but it's not huge. On the other hand, if we were only going, 15 feet, now you'd be losing 20% of your data. So that's just, you have to be mindful to purchase the right sensor with the right range and unmeasured blanking zone at the top. Okay, the next technology is relatively rare, although I see a lot of value in it, but it's just a very expensive sensor. But what's happening here is having a non-contact velocity measurement. So we put a radar above the water surface, and we measure the surface velocity as well as essentially the depth by measuring the distance from the sensor down to the water surface. When it floods, you're going to get closer to that, but as long as the flood doesn't put this underwater, you're okay. There are also some that have pressure transducers, so then you could also get the submerged depth anyway. But again, there's always a range resolution trade-off. So if you put this on a super tall pole, then you're safe, but you won't have the same resolution and range that you would get if you put it closer. So you have to figure that out. These are just relatively expensive, glorified float kind of technology. Of course, they can be data logging, which is really valuable, and they're not going to get hurt by sediment transport and stuff in the flood or woody debris, let's say. It's just you're only getting the surface velocity, so you need to calibrate that somehow to get to mean velocity. And the last thing I want to show you is a laboratory technology, not a field technology. It's called particle image velocimetry. What happens here is you have a laser, and in this case it's showing with a mirror, but basically you're creating a laser sheet. Remember from the distrometer that we use for rain, we also had a line light that was like also making a light sheet. Within that sheet, particles are illuminated, and so then you can add particles upstream, and as they go through the sheet, then you see within that one slice the two-dimensional flux, up, down, and downstream. So this allows you to then calculate velocity vector in that 2 dimensions. And here's just an individual ball on the bed, and so you can see the water making a recirculation around that, and you can see some of the turbulent complexity of the velocity field in the vicinity of that particle. Another thing we're seeing now is, imagine that this was a top view. People are now taking quadricopters and balloons with cameras, holding them in position over a river, and then either seeding with particles or using native particles floating in the water, and making plan view 2D maps of the flow field based on that imagery. And remember, I talked a little bit about that kind of thing with the structure from motion for geographic positioning. So this is another technology. So being able to get at the velocity field, if that's what you want, then this kind of image-based analysis is useful. And we're going to see that because this is being done quite a bit for commercial purposes outside of velocity measurement for science, then this is expanding very rapidly, and it may become very prominent in short order. However, the traditional methods with these electromagnetic and propeller meters, they're still here to stay for quite some time. These are the traditional sensors that are used. We're seeing more of these acoustic Doppler velocimeters and current profilers. You don't see the profilers used to get a specific velocity value, but to get the overall field, maybe even get the depth average value with more accuracy. Okay, so those are all of the methods, and we'll be playing with all this both in the lab and in the field so that you can see how these technologies work.